In this screencast, I'm going to talk to you about the single replicate of the 2 to the k design. And this becomes important when k is greater than or equal to about 4. Let's revisit the 2 cube design that we've previously talked about. This was a replicated design. We had n equals 2. In other words, for each of the treatment combinations, we obtained 2 responses or experimental observations over here on the right. For this, we have a total number of observations of 16. The total degrees of freedom is always capital N minus 1. That would give us 15 total degrees of freedom. In using those degrees of freedom, we can assign 1 degree of freedom to each of the 3 main effects, each of the 3 binary effects, and the 1 ternary effect. So that equals 7 degrees of freedom that we need in order to calculate numerical answers for those different effects. The other remaining 8 degrees of freedom we use as error, as an estimate for error. And so 8 degrees of freedom are assigned to error. Therefore, we have plenty of degrees of freedom for error to perform our statistical tests. Whenever you're performing statistical tests, you need plenty of additional equations or degrees of freedom to use as pure error in order to calculate test statistics. So let's take a look at this example if we had only had 1 observation per treatment. So I've removed that second replicate of each of these observations. In this case, we only have 7 total degrees of freedom. If we assign 1 degree of freedom to each of those 3 main effects, each of the 3 binaries, and to our 1 ternary effect, that's 7 degrees of freedom. This leaves us with 0 degrees of freedom for error. A statistical analysis in this case is not possible. Thus, for an unreplicated design, there are not enough degrees of freedom to perform a full statistical analysis since there are no degrees of freedom assigned to pure error. However, when k gets big, greater than about 4 or 5, it is quite common to perform a single replicate of the experiment. Why is this? Well, for example, a 2 to the 5th design, if you wanted to do an unreplicated design, that only requires 32 observations. So for each of the replicates in a 2 to the 5th design, you need an additional 32 observations. And you can imagine, in some experiments, 32 observations is quite a bit. That's a lot of time and money. The cost and time savings is significant if you can perform an unreplicated design. But as we mentioned earlier, you cannot perform a statistical analysis, a full statistical analysis. So how do we do this statistical analysis in a single replicate of the 2 to the k design? Well, there's 2 options that I'll show you in this screencast. There's a normal effects plot, and there's a sparsity of effects principle, both of which we can use to statistically analyze the significance of the effects. In option 1, we can create a normal effects plot. This is essentially a probability plot of the effects. Minitab can do this for us quite easily. What we want to look at in this normal effects plot is which effects do not fit in with the others. These are the potentially significant effects, and we can use the insignificant effects as error degrees of freedom. So let's go ahead and do this first option in Minitab. The data that we're going to be working with is in a file called Unreplicated 2 to the 5th Design. We could perform this analysis in Excel just like we've been doing for full factorial designs, but it's a little bit easier as the number of factors gets higher to perform this in Minitab. So I'm just going to go ahead and select all of this data, Control Copy. I'm going to go over here to Minitab and I'm just going to paste our data. The first thing we need to do, and this is an alternative to creating a factorial design, if I've already got the factor levels, -1 and 1 on the worksheet here in Minitab, you can go to Define Custom Factorial Design. Our factors are A through E. We can go to low, high. These are coded variables. We can select that. Everything is in standard order from Excel. And I can go ahead and click OK. And it adds these columns for standard order and run order, which we basically just ignore. But now we're ready to analyze the factorial design. We go to Stat DOE, Factorial, Analyze Factorial Design. Our response is Y. And the important thing here for this approach, for doing the normal effects analysis, the normal effects plot, is to go to Graphs and select Normal here from the effects plots. We actually don't need that Pareto plot, so I'm going to deselect that. Go ahead and click OK. click OK again, it churns through and does the analysis. And what you'll notice, first of all, in the statistical analysis, it's got all these stars here, which means it can't compute those values. And that's again because we don't have enough degrees of freedom for error. If you go down here to ANOVA, you see that at the very bottom it says we have 0 error degrees of freedom. So the statistical analysis of this is not possible when we're trying to get numerical values for all of the effects when we don't have enough degrees of freedom. But what we can do with that normal effects plot, this is pretty slick because it puts all the effects kind of in a comparison, but the ones that stick out, they're way outside of a normal probability plot of all of the others. Well, we can conclude here, the ones in red are significant responses, so that's A, B, the interaction AB, DE, and the interaction DE. And so those are the significant ones. If we wanted to calculate actual p-values now to perform a statistical analysis, we can go back into stat DOE, factorial, analyze factorial design. But now the terms, I'm going to deselect everything here, and I'm just going to select the ones that we identified in the normal effects plot, AB, DE, the interaction AB, and if we scroll down here, DE. And I'm going to add those by pressing on this button here, and then we can select OK. We can click OK again. And now what it's doing is it's going through the statistical analysis of just those ones that we put into our model, and it's coming out with a regression equation in uncoded units, which really is our coded units, by the way, because our data here is in coded units. The second option to doing a statistical analysis of a 2 to the k design is to use this sparsity of effects principle. And again, this is for when k gets big, when k is greater than 4 or 5. A system is generally dominated by the main effects and low order interactions. 3-factor and higher order interactions are typically negligible. Thus, the higher order interactions, 3rd, 4th, 5th, and so on, can be used as an estimate for the error. So we can use those 3rd through 5th order interactions as error degrees of freedom. For example, in our 2 to the 5th design, we have 5 degrees of freedom that correspond to the main effects. We have 10 degrees of freedom that correspond to 2-factor interactions. And we have 16 degrees of freedom that correspond to 3, 4, and 5-factor interactions. So what we're going to do with this second approach is we're going to assume that these 3rd, 4th, and 5th order interactions are negligible, and we're going to use those basically as our estimate for error. So over here in Minitab, we have the same data. We just have to set it up differently. I'm going to go to stat DOE, factorial, analyze factorial design, and we're going to go into terms here. And now what I'm going to do is remove everything by using this double less than sign to get them all back over here on the left. And at the top here, I'm just going to include up through order 2 in our model. So we're only considering main effects and binary effects. Everything else, the 3rd, 4th, and 5th order terms, we're going to assume are insignificant. And if we don't put them over here on the right, it just assumes we can use those degrees of freedom for error. And so we've got our selected terms. I go ahead and click OK. Click OK once again, and it churns through. And in this case, we do have error degrees of freedom, and it'll calculate p-values for those different main effects and binary effects. We come to the same conclusion that we got using the normal effects plot. A, B, D, and E, all those main effects are significant. The AB interaction is significant, and the DE interaction down here is significant. If you wanted to see if trinary effects are significant, we could go in there and we could remove all the effects and we could add up through order 3 in our model, and that's how we could do that analysis. So hopefully you learned a little bit more about performing a unreplicated 2 to the k factorial design in this screencast. Another option to performing an unreplicated 2 to the k design is to perform a fractional factorial design, and we'll be talking about that in some future screencasts.